Good afternoon. My name is Jakub Ratajczak. Welcome to my talk on the experimental falsification of the pilot wave interpretation of quantum mechanics. This presentation is organized as follows. First, I'll introduce a non-local gas model we use along with predictions derived from the model. Next, I will discuss the principle of the experiment we performed according to the model. I will present experiment results. Next, I will show why these results contradict pilot wave interpretation of quantum mechanics. At the end, I'm going to address briefly some other phenomena that may be related to this model. You may find more on this in the paper shown on the screen. Let me introduce the gas model. First of all, we work in the non-relativistic limit. We assume gas particles move slow enough. As in the ideal gas model, we treat particles independently. However, here we treat them as an independent wave functions. We apply the free-particle Schrödinger equation solution to each wave function. We assume this solution is valid during a particle-free time. There is no potential, no measurement, no collapse. This is why spontaneous spread occurs for each wave function independently. Note that mean free time may be very long for an ultra-thin gas. We will be curious, what if spreading, for example measured as a standard deviation, becomes bigger than a detector used for measuring transmittance of such a gas, the optical transmittance. But before we get to the transmittance, let's check conditions required for the model. This model applies to gas of any kind, atomic, molecular, mixed, etc. Just enough mean free time should be provided. Time from any interaction leading to wave function, free from any interaction leading to wave function collapse. It means rare collisions, no environmental disturbance, and no photons absorption. Please note that this is a kind of extended version of mean free time known from the ideal gas model. Interesting predictions arise from the model if wave functions are interpreted non-locally, the falsifiable predictions. Last but not least, we assume no gravitational decoherence. Now let me present two falsifiable predictions arising from the model. First, the transmittance of such gas depends on the size of the detector. For detectors larger than the wavelength, and macroscopic ones, the smaller detector measures higher transmittance. The transmittance may reach up to 100%, even for a huge cloud, a large number of particles, for a very long light path length. A cloud becomes transparent when mean free time grows, when spread becomes significant. You will see equations in a moment. And this prediction is tested in the experiment I will describe later on. The second prediction is that the environment influences particles' effective cross-section on any local interaction. It's a direct consequence of a wave function non-locality. The more wave function is spread, the less likely the particle is to be found in a finite volume. And we will call this model the smeared gas. This model is described in the paper shown on the screen. We want to work with transmittance, so we need to define it for a smeared gas cloud. Let's do it in the following way. Transmittance is a probability that a photon coming from source that would have been detected by the detector in the absence of this cloud passes non-scattered the entire cloud and is detected by the detector at the end. This is the first equation here on the screen, where Pn is a probability of scattering by nth particle. But a scattering event needs to take place in some volume where it may influence the detector at all. Look, clouds in Paris do not affect sun visibility in London. This is why the detectability tunnel T is introduced in the second equation. The second equation is the probability that a particle may be found in such a volume between the source and the detector. The G constant is a kind of dimensionless normalizing factor. It depends on the total cross-section for the given wavelength and geometry of the setup. This is distances from the cloud to the source and to the detector, etc. And it also represents constant internal structure of a particle, like a constant Einstein coefficients, constant total cross-section of a particle. And now let's integrate the second equation using the free particle Schrödinger equation solution. This is the exact analytic solution of the integral from the previous screen for a square detector and square source of the same size. They are set parallel to each other. Such a setup is shown on the picture on the left-hand side. The red square is a source of photons, the gray cuboid is a visibility tunnel. It's the volume where a scattering event may be detected or may affect the blue macroscopic detector on the right-hand side. There are also a few spread gas particles wave functions shown. The mean free time here is a time from any incidents that may lead to wave function collapse, namely collisions and photon absorptions. As you see, transmittance defined in this way depends not just on the density of the cloud and the particle cross-section, as we know from classic models. It depends also on the size of the detector and on the mean free time between collapses. And the mean free time depends on the strength of the electromagnetic field, and it depends on pressure. In the paper, we derived the classic exponential transmittance law, the Beer-Lambert law, as the first-order approximation of this particular equation. Here we've got a more realistic setup. We have a point-sized source of photons on the left-hand side. For example, an atom. We've got a few gas particles in the middle, and we've got the round blue detector. The radius of the detector is RT. There is no analytic solution for this setup, but we might present inequality that where the previous analytical solution is the lower limit of the measured transmittance. And this inequality leads to the prediction that transmittance increases up to 100% for any finite detector and a sufficiently long mean free time. See the orange curve on the plot. It's the transmittance as a function of mean free time. The animation and the plot are not to scale, they just show relationships, trends, limits, etc. The equation in this form is very computationally demanding. There is a simpler version presented in the paper. It gives an approximation to the desired accuracy. In the experiment, we are going to check if the transmittance depends on the size of the detector, the RT in our equation. For a macroscopic detector, the transmittance should rise for smaller diameters. And now let's get to the experiment. To check if the transmittance depends on the size of the detector, we designed a modified tunable diode laser absorption spectroscopy setup. There is a low pressure vacuum water vapor in a 300 liters vacuum chamber, two spherical mirrors in a multipass cell make light path length as long as 60 meters. The infrared tunable laser works in a water resonant wavelength of 1.36 microns. The laser beam is split at the end by a beam splitter towards two detectors. There are two identical photodiodes, each 200 microns in diameter, and one of them, number one on this picture here, is obscured by an aperture. The aperture is replaceable. This way we can adjust the effective diameter of the first detector down to 2 microns. In the experiment, we measured transmittances for 9 different diameters of this detector. Thanks to low pressure and big chamber, we estimate particle mean free time to be at least 0.6 milliseconds. It gives more than 14 micron standard deviation of wave function spread for water molecule. This way, the conditions for smeared gas are met in this experiment. And we measure transmittance of a gas in a chamber with both detectors in parallel. And if both measurements were the same, the model would fail. We'll check it later. In this setup, the detectability tunnel is of complicated shape. So, there are spherical mirrors, many bounces, detectors diameters comparable to wavelengths, etc. Therefore, we were unable to build a quantitative model yet. All results are compared qualitatively. Now, experiment results. These results of the experiment are presented as a transmittance quotient TQ. This is the dimensionless value obtained by dividing the transmittance measured with the first detector by the transmittance measured with the second, the bigger detector. The quotient equal to 1 means that both transmittances are equal, both measurements are equal. The quotient greater than 1 means that the transmittance measured by the first, the smaller detector, is greater. And this is our case here. As you can see on the chart, the quotient is always greater than 100%. The largest difference measured is that for the 50 microns aperture. Quotients for 5 different apertures are greater than 100% with more than 5 sigma statistical significance. All this is in agreement with the smeared gas model. As far as we know, there is no other gas or transmittance model that predicts such phenomenon. This single result is astonishing. But each point here is the result of many consecutive single measurements. Thanks to different pressure conditions during many weeks of experiment, we have bonus results. As I said a few slides ago, the smeared gas transmittance is pressure dependent. We analyzed with a toy model how the transmittance quotient should behave for different pressures. You can see these model predictions as solid lines on the chart here. Basically, for larger number of particles in the chamber, it is for higher pressure, quotient should be higher. This is the orange line here. For less number of particles, quotient should be lower. This is the green line here. We found in our experiment data appropriate pressures for 5 apertures, 2, 25, 40, 50 and 150 microns, where we were able to split measurements into 2 distinct pressure buckets for each of those apertures. And guess what? Quotients for higher pressure were always higher. See, the orange points are always higher than green points. And this is also in qualitative agreement with the model. Okay, how about the contradiction with the pilot wave interpretation? All these results contradict any local interpretation of quantum mechanics. Recall the detectability tunnel T is a volume where scattering event influences measurement. Now look, gas particles whose sizes are on the order of picometers, if treated locally, they are either completely inside this volume T, or completely out of it. It cannot lead to the prediction of the dependence of transmittance on the size of the detector. However, in the experiment such a dependence was shown. See the orange arrow here. In the conditions of this particular experiment, any local interpretation of quantum mechanics would lead just to another isotropic distributions of gas particles in the chamber. However, any isotropic distribution of well-localized small particles like small balls leads to the same transmittance. So transmittance quotient should be always equal to 1. But it is not. At the end, I'd like to present some other phenomena related to this model. Well, smeared gas is a form of matter that have excellent conditions in deep space. There's ultra low density, there is dark, there are no boundaries. It can take the form of huge clouds. They retain its mass, but they are fully transparent for our telescopes. Telescopes are just detectors of finite size. Non-local particles also stop interacting with other detectors of finite size like dust, planets or even stars. They become WIMPs. However, stars and galaxies' light might make cloud kind of denser in the vicinity of a source of light. And doesn't it look like a perfect candidate for dark matter? There is another almost local phenomenon that can be related to the smeared gas. Astrophysicists noticed the density of upper parts of Earth's atmosphere is sunlight dependent. The geocorona density drops on the shadowed side of Earth, and the density is also correlated with sun activity. Such a behavior is totally in agreement with the smeared gas model. So, smeared gas model seems to be a promising research field. We are preparing next experiments, we work on better quantitative models. We would like to check if there are phenomena explainable by this model. Thank you for your time and attention. If you are interested in this topic, you may find more information, including online experimental data and other materials, on our website. This is smearedgas.org. Thank you very much.